I will also start recording. So this is lecture number 11. We are now in the 6th week, 1/3 of the way through, very exciting. And we have the following question. In Professor Krugman's economic course, the correlation between the student's total score prior to the final and their final examination scores is R equals 0.5. The pre-exam totals for all students in the course have a mean of 280 and a standard deviation of 40. That's your X bar and your S sub X. The final exam scores have a mean 75 and standard deviation of 8. That is Y bar and S sub Y. And we were also given R is equal to 0.5. And Professor Krugman had lost Julie's final exam, but knows that her total before the exam score was 300. So he decides to predict her final exam score from her pre-exam total. Well, the only way you can predict it is once you have the best fit line. So in this particular example, we're not using the data itself to come up with the best fit line, but rather we are using the formulas involving X bar, S sub X, Y bar, S sub Y, and R. And they were in the PowerPoints. And the slope, if I remember correctly, is R S sub Y over S sub X. So if I take R, which is 0.5, and I multiply that by S sub Y, which was 8, and I divide it by S sub X, which is 40, I get a slope of 0.1. So knowing the slope is 0.1, I can already eliminate the first two options because their slopes are not 0.1. I have a text here. Let's see what it says. How do we do that on sapling? Because I don't have a calculator. Oh my, no, you can't use Crunchit because Crunchit requires the data and we don't have the data. We got to do it from the formulas. So you do got to find a calculator. You can do an online calculator. You don't need a physical one yourself, but this is a calculator problem. So now we know that the slope is 0.1. And then we need the y-intercept. And the y-intercept was, I think, y bar minus slope x bar. So the y bar is 75 minus slope, which is 0.1, times x bar, which is 280. And we get a y-intercept of 47. So the answer is y hat equals 47 plus 0.1x. I'm a science nerd, so I don't have any math stuff on me. Well, I'm a science nerd and a math nerd. And I got no follow-up. So the answer is y hat equals 47 plus 0.1x. So you are Thanos. I don't know what that means, but I appreciate it. Now I know Thanos is that guy from that movie and stuff who died at the end. So you're saying I'm going to die? I don't know what that means, but let's move on. Which of the choices is the correct interpretation for the slope, of the slope in the context of the problem? 0.1, that means for every 1 unit this way, I go up 0.1 units. What is the X referring to? The pre-exam score. What is the Y referring to? The post-exam score. So for each point of a student's pre-exam score, then on the average, the post-exam score and the final exam score is going to go up 0.1. So it is the first option there. And then use the regression line to predict your final score. Then you just plug in 300. 300 times 0.1 is 30. 30 plus 47 is 77. So if my prediction is correct, you will get a 77. Now, Julie does not think that this method accurately predicts how well she did in the final exam. Select a statement that correctly uses R squared to argue that her actual score could have been much higher or much lower than the predicted value. So if R is 0.5, then R squared is 0.25. So the third one is out. R squared is either 0.25 or 0.25 or 0.25. So this one says, since it's close to 0, or not exactly 0, or just positive, so 3 senses. Let's look at the first one. Since it's close to 0, the regression line does not predict final scores very well. Julie could have a much higher or lower score. Since it's not exactly 0, the regression line does predict final scores very well, and it could have been much higher or lower. And since R squared is positive, the regression line does not predict final scores very well. Julie could have a much higher score. Well, first of all, this makes no sense. R squared is always going to be positive, unless R is 0. But in general, R squared is always going to be positive. So this one's nonsense, just right off the bat. And if it's not exactly 0, We know that the closer it is to 0, the worse it does. So if it's not exactly 0, the further away from 0 it gets, the better predictor it gets. This doesn't really make sense at all. But we do know that an R of 0.5 means what? R of 0.5 tells me that the correlation is what?
Moderate.
Moderate or weak, right? It's on the border of moderate and weak, correct? So it's like very weakly moderate or very strongly weak, whatever term you want to use. But it's so close to being weak that she can legitimately say, listen, this might be what the data tells me, but the correlation is weak, and I don't accept this possibility. So the answer is certainly A, right? 25% R squared, very small. So does that make sense for that question? I hope it does. Since it's 0.25, it isn't strong, meaning that it is unlikely to be exactly on the line. The stronger it is, the more accurate the line is predicting future data. Yes, exactly. If we had a very strong R value, then that means pre-exam scores and post-exam scores are very strongly correlated. And if they're very strongly correlated, then knowing one should give us the other. But if they're very weakly correlated, then knowing one doesn't really predict the other one very well, because there's a lot of room for error. So it could be higher, it could be lower. It's got a weak correlation. Does that make sense? So someone said, can we go over question 14 or 13? Number 1, part B, please. Number 1, question 1? For the same homework, question 1? All right, well, before you, someone said, can we go over 14 or 13? So let's look at 14 or 13. Let me share it again and look at, where did it go? 14 or 13. So let's close this. And which one, 14 or 13? Pick one, verbally, because I can't see text.
13.
13, okay. Suppose Wesley is a marine biologist who was interested in the relationship between the age and the size of male male something crabs. Wesley collects data on 1,000 crabs. Oh, it's a big, pretty large sample, and uses the data to develop the following least squares regression line, where X is the age, and Y is the predicted value of, and Y hat is the predicted value of Y, the size of the male crab in centimeters. So Y hat is a function of X, and we have a regression line. Here is the slope, and here is the y-intercept. And we know nothing yet about the correlation, how strong it is. All we know is that this is the best fit line. So what's the value of y hat when the male crab is 9118 months old? Well, X is the age of the crab in months. So if the age of the crab is 24.9118, you plug that in for X, you do the math, and out pops the answer, 19.47. I'll assume that's correct. I'm not going to do it myself. Interpret the value of y hat, the predicted size of a crab when it's 24.9118 months old is this, right? Y hat is not the actual age, because all we have is the best fit line, which is a prediction line, correct? It can't tell me the actual age. I have no idea what the actual age is. The line is a best fit line through all of the data, and it just gives me the best prediction possible. Does that make sense? You just plug it in. Yeah, I don't see text when I'm sharing my screen, so sometimes if I don't see it till afterwards, I am sorry. And then someone said, can we do 13? Or sorry, 14. Can we just do 13, right? So let's see what it says. Homicide and suicide are both intentional means of ending a life. However, the reason for committing a homicide is different from that of a suicide, and we might expect homicide and suicide rates to be uncorrelated. On the other hand, both can involve some degree of violence, so maybe there is a correlation. I don't know. So what do you do when you don't know? You take some data. Am I sharing my screen right now? I don't think anyone sees it. So, all right. So maybe they are correlated. Who knows? Let's take a look at the data. The data from 08 to 11 for 26 counties in Ohio are shown in the table. These rates are 100,000 people. So the homicide rate is 3.8, means 3.8% of 100,000 people. Every 100,000 people had 3.8 homicides and 9.9 suicides, and so on. It says to access the complete data set, click the link for your preferred software format. So it says make a scatter plot. Okay, well, I know how to use scatter plot. I'll go to Crunch It. And then I'll go to graphics. I'll say scatter plot. And I'll say X is my, because there's 3 columns here. So X is homicide and Y is suicide. Is that what they want? Well, let's take a look. How do I get rid of this? How do I get rid of this thing? Oh, there we go. Okay, so that shows how suicide rate can be predicted from homicide. So homicide's on the x-axis. Good, we picked it right. So that's, oh, look at that. Anyone see a line there? Anyone see a good linear fit?
No.
No.
I don't see one. So my guesstimate is that R is going to be pretty small. Look at this. There's a weak linear relationship with R at 0.17, very small. Now, each of the scatter plots in the choices had a relationship fitted to the plot. Select the plot that corresponds with the correlation of 0.115. Well, first of all, okay, well, this one's certainly out because this is on a line. You don't get the option of just halfway through changing it. This one is fairly flat. This one is fairly positive. This one is fairly negative. So if you remember the formula for the slope of the best fit line, the slope is equal to R SY over SX, correct? That's the formula for the slope of the best fit line. Now, these are standard deviations, so they're always positive, which means if R is positive, then the slope has to be positive. Well, this is a negative slope, so that one's out. And this one has a positive slope, so that's certainly a possibility. And this one looks like it's 0 to negative, so it's got to be the only one with a positive slope, which is this one, and that's correct. Then it says find the least squares regression line for predicting the suicide. Well, we can go back to crunch it, and we say statistics, regression, simple linear, give me numerical results. The dependent variable is suicide, the independent is homicide, and it gives me 11.64 plus 0.1259x. 11.64 plus 0.1259x. So the slope is 0.126. Explain in words what the slope means. That means for every one this way, we go up 0.126. For every one what? 100,000 people. The slope means that for every additional homicide per 100,000 people, sorry, not people, this is homicide. For every additional homicide, the suicides go up by 0.126. So for every additional homicide for 100,000 people, there's an average increase of 0.126 suicides per 100,000 people in these Ohio counties because we don't have any other information. Now, another Ohio county has a homicide rate of 8. What is the country's predicted suicide rates? You just go back to your equation, which is in crunch it. You go back to your equation, you plug in 8 and you calculate your suicide rate. And you get this, and that's it. So I hope that made sense. And then someone says number 1, part B. This will be the last one because we got to move forward. So 1, part B. Let's share again. And oh, this is the one with the whole. Oh, it's a different one. Okay. How sensitive to changes in water temperature are coral reefs? To find out, scientists examine data on sea surface temperatures and coral growth per year at locations in the Gulf of Mexico and the Caribbean Sea. Scientists examined data on mean sea surface temperatures and mean coral growth over, okay, whatever, you got these things. It says use software, excuse me, use software to find the mean, the deviation of both of these things and put everything in here. So X bar, SX, Y bar, SY, and R. And then for B, it's just the formulas again. right? The formulas were R equals, sorry, the slope equals R SY over SX, which we have all three of those above. And then the y-intercept is equal to y bar, which we have, minus the slope, which we just calculated, times x bar. And you plug them in and you get the answers. Okay, so I did good that, but I got a different answer. Well, if that's the case, I would recommend checking again. And if it still doesn't work, we can stay after class a couple minutes and take a look at it. Is that okay? Hopefully it's okay, because we're already half an hour into class and we got to get started. So, okay. So we are moving ahead. We did 1 to 5. We skipped to 8. And now we are jumping ahead to chapter 15. And 15 starts, and I want to look at the sapling again. 15 really is the beginning of statistics, because what we've done so far, a lot of the basics, and I'm not saying they're not important, they're important, but 15 is 's more important. Yeah, so we're jumping into chapter 15. And you should all know, I did purchase a doc camera, a document camera. It just has not yet arrived yet. So when it does, hopefully it'll be easier to convey information. So chapter 15. Sorry, excuse me. Is on sampling distributions for a proportion. Sampling distributions for a proportion. And if you have the book at home, or you have the ebook, it is in my book on page 334. Oh, wait a second. I can share mine with you. Hold on. I have an ebook right here. I don't need this one. Oh, yeah. Modern technology. Okay. Chapter 15. So we have the basics down. The basics of statistics, how to visualize statistics and how to, graph different types of situations and best fit lines and things like that. But the core of statistics, when it comes to its utility, is one of two things: confidence intervals or hypothesis testing. And the next portion of the course is all about confidence intervals. And confidence intervals is lots of formulas that you don't have to memorize. All you need to do is know when to apply each formula for the situation that you apply it, plug in some numbers, and bam, you have your confidence interval. Or even better, have Crunch it do it for you. At its core is the following, right here. At its core is the difference between a parameter and a statistic, okay? A parameter is a number that describes the population. So for example, if I'm interested in the average height of every single American, that value, that average height of every American, that's a parameter because you're describing the entire population. In practice, the value of a parameter is not known because we can rarely examine the entire population. All right? How are you going to check every single person? Even if you can somehow manage to do that, by the time you're done, people will have probably changed heights to some extent or died or born. It's not feasible. And even if you say, no, you know what? We can do it. I'll say, fine, let me change the problem. Suppose we want to know the average mass of every star in the universe. No matter what you do, it's impossible to get that one. So the parameter is the actual true value of something. It's almost impossible to know it. So the best that we can do is come up with a statistic. A statistic is a number that can be computed from the sample data that does not make use of any unknown parameters. If we don't know them, we can't use them. Right? How are you going to use the average mass of every star in the universe if we don't know it? The best we can do, and in practice, what do? Is we often use a statistic to estimate an unknown parameter. So if I decide to take a sample of 100 people and compute their average height, I'm using that average height as my approximation of my guess for the average height of every American. The average height of my sample, that's a statistic. The average height of every American, that's a parameter. I'm going to use the statistic and say, well, because the statistic is 5 feet 8 inches, I'm going to make a good guess that the average height of every American, my parameter is 5 feet 8 inches. Is it exactly that? Probably not. Is there a little range around my value that I can be relatively confident that the true value is in that little range? Yes. Hence, confidence intervals. Are there any questions so far on the preliminaries of what we're getting into right now? Does it make sense so far? Are there any questions?
I have a question. I'm still kind of confused about this, like the unknown parameters part of it.
What are you confused about?
Like, how would you find like a sample of the data without knowing the parameters? That's what's confusing me.
Suppose you want to know the average height of every American. Is it possible to calculate that?
No.
No. So suppose you said, okay, I'll take a sample of 100 people and find their average height. Can you do that?
Yeah.
Not too hard, right? What you just found is a statistic. What you don't know that you wish to know is the parameter.
Got it.
You're going to use your statistic as a guess for what the parameter is.
Okay. Yes, it makes more sense. Thank you.
Okay. Someone just said something in text, but what did I just press? Never mind, that wasn't bad. So a parameter uses the population, like a survey, while a statistic is numbers derived from a set of data. Yes, but no, because even a survey might not get everyone. A census is better. When we do a census, by its very definition, you're getting everyone. So the United States Census every 10 years, that's everyone. Or at least everyone that can be reached, which is still not everyone. So a big form of analysis. Well, you don't need to use statistics if you have the actual value. Statistics is all about using samples to approximate or to guess the actual value. And, you know, that's the whole point. Of course, whenever you use a sample to get an approximation for the actual value, there's always going to be some uncertainty involved. How close is this value to the real thing? We'll get into it. So let's look at this example. It says the mean income of the sample of 124,586 households included in the current population survey was X bar. The sample mean was $75,738. This is a statistic because it only describes a number that comes from a sample. The population that the pool wants to draw conclusions about is all 125 million US households. We didn't use 125 million. We use roughly 125,000, which is 1/1000th of the entire population. The parameter is the mean income of all these households, and we have no idea what that parameter is. So, in this class, we are going to focus the majority of our time on two situations. Knowing X bar, but wanting to know the mu, the mean. So situation one is knowing the sample mean, the average of my sample, and wanting to calculate the actual mean of the entire population. And situation two is knowing my sample proportion and wanting to know the actual proportion. These are the two situations that we're going to deal with. We have a sample mean, we want the actual mean, or we have the sample proportion and we want the actual proportion. Okay? And we're going to start this chapter, I think, with, we'll take a look. So are there any questions so far on section one, which is just a difference between a parameter and a statistic? And just another possibility, although we're not going to do much of it, if at all, is this one, where we know the sample standard deviation and we want to know the actual standard deviation. Those are the three basic scenarios. So let's go to 15.2. Statistical estimation and the law of large numbers. So if you flip a coin one time, are you more likely to get a tails or a heads?
They're even.
They're even, right? What if you flip a coin 1,000 times? Are you going to claim you're just as likely to get 0 heads as 500 heads?
Yeah.
Yes, I mean, in your experience, if you flip a coin 1,000 times, is no heads as equally possible as 500 heads? Does that seem, forget about math, does that seem reasonable? That no heads at all
No.
is just as likely as 500 heads?
No.
No, I mean, 500 heads, if it happened, you'd be like, okay, I can see that happening. But if 0 heads happened, you'd be like, okay, what's going on here? This coin is certainly not a fair coin, right? 0 heads out of 500 flips is extremely different than 500 heads out of 1,000 flips. Even though on any specific flip, there's no way of knowing what's going to occur. But as the number of flips increases, we do have certain expectations. And if the numbers are not near those expectations, we'd be very shocked and surprised, correct? The law of large numbers says that as the number of trials increases, the proportion of times an event occurs gets closer and closer to whatever its true value is. So if I flip a coin 10 times, can I get 5 heads if I flip a coin 10 times? Would you be shocked if you got 5 heads and 5 tails?
No.
Okay. How about 4 heads and 6 tails?
No.
How about 3 heads and 7 tails?
Possible.
Possible. If it happened, would you say, this is crazy? Would you say that? Or would you be like, okay, didn't see that one coming, but certainly a possibility?
Second one.
Yeah, I mean, listen, even no heads. Do you know what the likelihood of getting no heads is on a flip of 10 coins?
Tails now.
It's basically 1 in 1,000. It's basically 1 in 1,000. It's close to that. It's a little worse than 1 in 1,000. It's actually 1 in 1,024. But if something happened that was a 1 in 1,000 chance of occurring, would you be surprised?
Yes.
I would.
Yes.
I'd be surprised. 1 in 1,000, I'd be surprised. Now, if somebody said, "I'll give you $1 million," all you have to do is hit this button. But here's the thing: there's a 1 in 1,000 chance that when you hit the button, you'll get electrocuted and die. Would you do it?
Yeah.
You would?
Yeah.
Wait, how much money is it?
$1 million,
That's not enough.
and there's a that's not enough.
I mean, it's a win-win.
Okay, so it's a 1 in 1,000 chance, but $1 million is not enough for you to take that risk.
Well, I mean, it's 2020. What do we have left?
I mean, you're not going to get the full million after taxes.
Okay. All right. Let's say it's 2 million, and after taxes, it gets 1 million. I mean, let's not worry about the details like that. The point I'm trying to make is that a 1 in 1,000 chance, yeah, it's 1 over 10 to 2 to the 10. A 1 in 1,000 chance is very unlikely, but not so unlikely as to you to risk your life over it. I would think for the average person. I mean, I've made this analogy in every class that I've ever taught in statistics, and one student said, "For $1 million, I'd go 1 in 5." And I'm like, "Really?" He's like, "Yeah, I do it 1 in 5." He'd be happy with a 20% chance.
It's Russian roulette right there.
Huh? What?
Russian roulette.
Basically, yeah, that's what it is, right? Russian roulette is, the gun. You put 1 bullet, you spin it, and then you pull the trigger. That's basically what it is. And I don't know anyone's ever played it and survived to tell me the tale, so I don't even know if it's a real thing, but that's what it is. But the point I'm trying to make here is as follows. On any individual, the energy from this class is immaculate. Thank you. I don't know what that means, but it sounds like such a compliment. So thank you so much, Wood Carly. It's beautiful. I'm crying inside, but I'm too strong to show it. So that's why I'm coming across as being very but really on the inside I'm tearing up. So what the hell does cat mean? So lying. Cat means lying. I am
Like that's cap.
Yeah, that doesn't explain anything.
Okay, so like you saying that you have bad style, I would say that's cap because you have great style.
Oh, so why don't you just say, I don't know. I don't get slang sometimes. I really don't. I mean, my generation also had slang. I didn't get it then either, but I used it, right, bruh? Anyways, let's move on. So I still don't quite, your fit is a straight, drippy. Wow, I don't know what anyone's saying right now. It's like it's English, but at the same time, it's not. It's quite weird. And that's poggers, right? No, that doesn't make sense. I heard that the other day. Okay, whatever. So let's move on. So the law of large numbers says as follows. You don't know what you're going to get on any one specific flip. Glizzy Cup. You don't know what you're going to get on any one specific flip, but in the long run, the proportion of occurrences is going to approach whatever the true value is. Here we go. Law of large numbers. Draw observations at random from any population with finite mean mu, whatever the true mean is, which you don't know, it's a parameter, as a number of observations drawn increases. The mean x bar of the observed values tends to get closer and closer to the mean mu of the population. In other words, if I want an average height of every American, and I take 3 people and compute my average from those 3 people, do I really have strong expectations that my sample average is close to the actual average?
No.
No. But if it was 300 people, or 3,000 people, or 300,000 people, or 3 million people, then I would expect that as the sample size increases, it gets closer and closer to the true value. That is the law of large numbers. And it can actually be proven mathematically, which we're not going to do because the math is way too advanced for this class. All right? It needs calculus and even some math beyond calculus. So we're not going to worry about it. Okay? But just conceptually, we do have to understand it. Conceptually, it just says that as a sample size increases, the sample value, your statistic, will get closer and closer to the population value, the parameter that it is approximating. Okay, does that make sense? Here's an example of the number or the mean. So I don't know exactly what the situation is, but there's some situation where people are computing the mean of 1 observation, of 2, of 3, to 5, to 10, to 50, to 100, to 500,000, so on. What you see is in the beginning, when the mean is small. Yeah, Anthony, it's very logical, but it's always nice in math when you can prove things even when they're logical. So what you have here is as follows. You have a lot of fluctuation in the beginning. The thing is all over the place. 28, 34, 32, back up, down, up, down. What you see as the number of observations increases, it eventually stabilizes. And it's always going to vary a little bit. It's never going to be just the same value forever. But in general, as the number of observations increases, it will stabilize around this true value. So whatever this particular problem is dealing with, and I guess we can look if I really cared. Yeah, so it goes, suppose the distribution of odor thresholds among all adults is mean 25. I don't know how you quantify odor thresholds, but suppose there's some way to quantify it. Then that means that for any small sample, you might be all over the place, but eventually it should stabilize around 25. So the law of large numbers is illustrated in this diagram by fluctuation followed by stabilization around the value that you expect. That is what the law of large numbers is, and that's all you need from this particular section. So, section 3. Sampling distributions. Now, sampling distributions is where we begin doing math. Okay? Remember what a distribution is, right? A distribution is a curve that we draw to represent the possible values that something can take, right? So here we have this distribution here, this density curve or this distribution. According to this, where are you most likely to fall? If I give you one observation, where are you most likely to fall?
25.
Around 25, where it's the highest. And then you expect that as you differ from 25 in either direction, you should get more and more likely, less and less likely, sorry, so that fewer observations occur around 20 or 30 than around 25, right? Now, this is one observation at a time. So someone asked, it's sort of like an asymptote. What do you mean it is like, or you didn't say it, you said sort of like an asymptote. You should say the law of large numbers, we're back to that one. Yeah, so the law of large numbers, you can imagine it as being very asymptotic, but it's not a nice smooth curve necessarily. It's always going to have some variation. But yeah, it is in the sense that we expect it to converge to a specific value. Now, if I were to take a sample of size 1, then it's most likely to be 25 and not so likely to be 20 or to be 30. Would you agree? For whatever this particular distribution is referring to.
Yes.
Now, what if I took a sample of size 2 and I told you to average your values? How likely is it that your average would be near 25? Would that be relatively high or relatively low for the average of 2 values from this distribution to be about 25? It would be high because, first of all, you expect each one to be 25, so their average will be 25. But even if you end up with a 20 and a 30, the average is going to be 25, right? So what happens is that there's more situations where you might get a 25 average. Now, how likely is it that the average is going to be 20? If I take in 2 people and each one is extremely unlikely to be 20, how likely is it that the average of them is going to be 20? Are you guys kind of following what I'm saying?
No.
Pick a number at random from 20 to 30.
25.
25. Pick another one at random.
27.
Okay, what's their average?
2. 20.
The average 25 and 27?
26.
26, right? Halfway in between, 25 and
Oh,
27.
my bad. Yeah.
Okay. Now, if you were truly picking numbers from 20 to 30 at random, then that would be a uniform distribution, right? Anything is equally likely. Okay, but this situation is not uniform. In fact, I'm gonna go off attendance for a second. So law of large number. No, sorry. I'm gonna use central limit theorem. Okay. Can you all see this? Okay. So here we have a situation where the underlying distribution is this shape. What kind of shape is this?
Bell.
That's a bell curve, right? And if I take one at a time, I expect to have lots of them occur in the middle and not so many occur on the edges, right? How many samples did I take for this particular problem? For this particular,
31,000.
right, 31,427. So 31,427, most of them occurred right here in the middle. And as I tapered off to either side, it kind of dropped. If I do a distribution that looks like this, where every number is equally likely, then if I also do roughly around 31,000, what's the shape going to be? How high is each column going to be if the distribution is uniform? What do you expect?
About half.
I'm sorry? I'm saying what would the shape look like?
Oh,
Right?
Like a box.
It would look like a box. Could you be even more specific?
They all have the same height, right? So,
So,
it's-
well, yeah, so they all have the same height here according to my curve, which means the amount that fell in each of these columns should be roughly the same, right?
Yeah.
In which case, what would the shape be when I graph it? What should it look like?
If all the values are the same amount.
If every one of these numbers from 0 to 100 is as equally likely to be picked as any other one, and I do something like 30,000 choices at random, then how high will each of these columns be when I graph it? So
Wouldn't it all be the same height?
well, it should be approximately the same height, right? You're never going to get a perfect, this is 30,104 observations, right? You're never going to get a perfect uniform because this is a real life simulation. If I did it again, it'll look like this. If I do it again, it'll look like this. It's all pretty much the same, correct? What if I did this weird looking one, number 3, which was very likely to be on the left side, somewhat likely to be on the right, and not very likely to be in the middle? When I graph that, what do you think the columns are going to look like? How many of them are going to be here? How many are going to be here? How many here? How high are each column going to be? What should it look like when I graph it? What do you expect?
Wouldn't the majority be on the left? Some of them will be on the right, and then the rest will be in the middle.
Right? Looks like that, correct? Right? It kind of mirrors the shape, does it not? Lots of them over here, not so many over here, some over here, and then we have columns that kind of back that up. Now, let's do number 4. Very likely to be in the left, very likely to be in the right, very unlikely to be in the middle. What's it going to look like?
A V shape?
Seems reasonable, correct?
Yes.
Okay, now here's the question. Sort of like a reverse bell curve. Now here's the question. What if instead of a sample of size 1, I change it to having samples of size 2? But let's understand what that means. I take 2 of them at random, compute their average, and that's what I plot. I plot their average. So if I get a 40 and a 60, what would I plot?
50.
I'd plot
50.
50. And if I got 0 and 100, what would I plot?
50.
50. And if I got 0 and 0, what would I plot?
0.
0. So the question is, so let's start with an easier one. Let's start with number 1 instead. So let me do 1 again so we know what it looks like. And let's increase it to 2. So the question is, if I average them and then plot their averages, what's it going to look like? Where do I expect it to be high and where do I expect it to be low?
Do you expect it to be high in the middle?
Okay, and where would it be low?
On the tails? On the left side and the right side?
Yeah, because the only way for the average to be 0 would be if both of them are 0, right? And if it's truly uniform, then it's kind of unlikely for both to be 0 or both to be 100. It's much more likely for, on the average, for them to add to 50. So let's take a look at what it looks like. Does that seem reasonable?
Yes.
What if I increase it to 5 and I did the average of 5? If you
It
took,
would be a steeper, oh, sorry.
yeah, go ahead.
I would assume it would be a steeper mountain shape. Yeah.
And how about 10?
Same, just a lot more steeper.
And how about 20? What do those look like to you?
It eventually starts looking the same.
It eventually starts looking like a bell curve.
Yeah.
What if I start with a bell curve? So they're all bell curves, but what do you notice about the bell curves? What's happening as a number, as the size gets bigger? As I take,
Gets higher. The average is higher.
well, the average is staying around 50. Is that what you meant by higher, or the column height is higher?
Like the height of the column.
Well, it still looks like it's going to the top of the graph, but I think the key is it's getting thinner. Right? It's getting thinner. Because if you take an average, it's much more likely, the higher the sample size, the much more likely it is to have the average in the middle versus on the, I mean, here it's basically 0% up until here. Even something that's very non-normal looking, if I average these and I take a sample of size 5 or even 10, look at this. When the sample size increases, it just gets more and more like a normal curve. Even let's look at the number 8 here. Right? If we do a sample of size 2, size 4,
So, Professor,
yeah.
basically, the more you increase the sample size, the more often than not, it's going to become a normal bell curve.
Well, we're going to learn that very shortly. It's called the central limit theorem. And the
Okay.
central limit theorem basically says that, right here, section 5, so we're very close. The central limit theorem says that as the sample size increases, it makes no difference what kind of shape you began with. The sampling distribution is going to look normal. It's going to look like a bell curve. But we have to understand what that means. So I wanted to give you that picture so you can look at it and keep it in mind as we talk about sampling distributions. Okay? If you take, well, thank you, Vanessa. If you take one observation from this population, it's very likely to be 25, correct? I mean, 25 is the peak, so it's more likely to be 25 than anything else, right?
Can you scroll down a little bit?
Yeah.
Oh, you can't see it?
There we go.
Okay. So if you take one observation, it's most likely to be around 25, right?
Yeah.
Do you know in advance what it's going to be?
No.
Of course not, right? If we did, we wouldn't, I'd be in Vegas right now, right? We don't know what it's going to be in advance. Now, if you took 10 of them and averaged the 10, what's the most likely outcome that it's going to be? The average.
Around 25.
Around 25. Do you know what the average is going to be in advance?
No.
No. So just like for one at a time, we do not know what it is in advance. So therefore, we have to have a distribution to describe it. Also, for samples of a given size, we don't know what it's going to be in advance. So we have to have a graph to describe it. This gets us to the difference between the population distribution and the sampling distribution. The population distribution is when you do one at a time. It is the distribution for the entire population where every individual is one occurrence. I take one at random, most likely to be 25. Or it could be this, or it could be that. The sampling distribution, on the other hand, is when you take samples of a given size. So all possible samples of the same size. So I'm curious, if I take a sample of size 10, what's going to happen? So what do? We analyze every possible sample of size 10 that you can possibly get. And we look at how often each value occurs, and we have a graph to describe the data. That's called the sampling distribution. And as we saw in the diagram, in the applet that we just went through, no matter the shape of the individual population, no matter the shape, even something as weird looking as this one, which we didn't look at before, if the sample size gets large enough, it will eventually look normal. That's the central limit theorem, which is the subject of a couple sections from now. But the point is that not only does the original distribution have a shape, the sampling distribution of a given size also has a shape, okay? And we're going to talk about its center, its variability, all the things that we analyzed in the first few chapters. We can ask the same questions about the sampling distribution. But luckily, we don't have to, because we're going to have formulas, and the formulas will give us all the answers. So let's jump right into the very first one, the sampling distribution of X bar, okay? So we'll start with case 1. This is our first important result. Suppose that X bar is the mean of an SRS. So condition 1, it has to be an SRS. So we have an SRS of size n drawn from a population with mean mu and deviation sigma. It says nothing about being normal. It just says, suppose you have an SRS from a population with parameters, because remember, parameters refer to the entire population, with parameters mu and sigma for the mean and deviation. And standard deviation. So X bar has mean mu. It has the same mean, but its deviation is different. What is the deviation, the standard deviation of X bar in comparison to the standard deviation of X itself? If X comes from a distribution of mean mu and standard deviation sigma, then what does X bar come from? Mean mu and deviation what? It's literally written there on the page. Anyone? Can anyone read it off the page? It's okay. Your silence allows me to eat. Anyone? It's in the box.
May you repeat the question one more time, please?
Suppose X is something from a population whose mean is mu and whose standard deviation is sigma. The question is, what is the mean and standard deviation of X bar of a sample of size n? What is the average mean value going to be, and what is the standard deviation of the average value going to be?
The mean is going to stay the same. It's going to be mu, and then the standard deviation is, I think it's sigma, you said, right?
Well, the original one was sigma.
Divided by the square root of n.
That's it. It's right there in the box. Right? So if the mean is mu and the standard deviation is sigma, for X, the original one, then X bar, why does it keep doing that? Then X bar has the same mean, but what happens to the deviation? What happens to sigma, to the standard deviation of X bar as the sample size gets larger?
It gets smaller.
It gets smaller. Does that seem reasonable?
Yes,
Why?
because it's just like what you told us with the law of large numbers, that it starts to average out, gets closer to its true value.
Exactly. As the sample size increases, the amount of fluctuation around the true value decreases. And that manifests itself in this formula, which says that as n gets larger and larger, the deviation, which is the spread, gets smaller and smaller as a factor of 1 over the square root of n. So if my sample is size 100, let's say, then the deviation will be 10 times smaller because I will divide by 10. Because the square root of 100 is 10. Does that make sense? Yes? No, maybe so?
Yes.
Okay. So as a consequence of that, we have the box on this page. If the individual observations, if X comes from a normal with mu sigma distribution, then X bar also has a normal distribution, the same mean mu, but a smaller sigma. In this case, it's sigma over the square root of n. If it's not normal, then you cannot immediately conclude that X bar is also the same. This is true only for normal distributions. If the original one was normal, then X bar is also normal. If it was not normal, You cannot do that. Unless n is so large that it looks normal, as we saw in the applet. In the beginning, it looked kind of weird, but as n got bigger, it looked more and more normal. The only time that it is normal and then you increase it and it's normal, and you increase it and it's normal, and you increase it and it's normal, is if it starts normal. By the way, look what's happening to the spread as n gets larger. What's happening to the width of this as n gets larger?
It's smaller.
It's getting smaller, right? The sigma is getting smaller. When I go to 30, which is the highest this applet can go, you can see it's very steep. Whereas the original one, which is 1, I guess we can probably start over, is much wider. So let's do an example. If we measure the DMS odor thresholds of individual adults through some quantitative means, the values follow the normal distribution with mean mu equals 25 micrograms per liter and standard deviation sigma equals 7. So what we have here is an n. That was a horrible n, but we have an n. It's getting worse. 1 second. So we have an n of 25.7. Correct?
Yeah.
Now, we take a sample, specifically an SRS of size n equals 10. So this is x. And now we want the distribution of x bar. So it's also normal, because that's what this box says. If we start normal, x bar is also normal. It's still going to have a mean of 25. But what is its new sigma going to be?
It would be 5.
Why 5?
Are we taking the square root of 25 for the mean?
Well,
Now?
no. It's the square root of n, not the square root of the mean. N is the sample size. N is 10.
It would be 2.2136, right?
Well,
Because
yeah,
you plug it into the equation.
right there. Can you see it? .2136. Someone texted to me. They were correct. Right? Yes, no, maybe so.
So that equation would essentially be the mathematical way of the visual calculator that you're showing us. As the sample size increases, the mean gets smaller.
Well, the mean does not get
Well,
smaller.
I mean the standard deviation.
Right, but the deviation gets smaller.
Yeah.
So here's a picture that describes the original one. The original one is for one person. One person on the average will be around 25 and will be less likely to be in the wings. But if you take a sample of size 10, you're now much more likely to be around 25 and much less likely to have your average on the wings. The mean stays the same, but it squeezes and gets taller. Okay? Does that make sense?
Yes.
Yes.
So let's move now to the central limit theorem. The central limit theorem is extremely important. And this is exactly what the applet described. It's a draw an SRS of size n from any population, not just normal, anything with mean mu and standard deviation sigma. The central limit theorem says that when n is large, The sampling distribution of X bar is approximately normal with exactly the same formula. Mean mu and sigma over the square root of n. If it's normal, X bar is exactly normal. If it's not normal, X bar is approximately normal. How big must it be before you can say it's pretty normal? So let's look at one that's decidedly not normal. Which one of these is decidedly not normal should I use?
4. That's not normal.
Okay, 4 is certainly not normal, right? It's extremely not normal, correct? Okay, so we'll start with number 4. If I do 2, is that normal?
No.
3, is that normal?
Nope.
4, is that normal?
Getting there.
But not quite yet, right? 5,
Almost.
6.
Yes.
All right, so you're saying by 6, we're already close enough to normal that we can say this is normal. Let's see how much we need for 8. Would 6 be enough for this one?
No.
It's long to the right, correct? How about we go to 8?
No.
10?
No.
15?
No.
20?
No.
25?
Was it supposed to be moving over to the right?
No, it just has to be normal looking. Doesn't have to be here. It can be anywhere. It just has to be normal.
Oh, I see. In that case, then yeah, it has been.
Oh, it has been. So let's go back. 20?
Yeah.
15?
Yeah, that's normal.
Yeah.
All right. 10?
That's not normal.
Okay, let's try 3. How many did it take for 3? Let's go to 5. Already is pretty close, right? So even these
That's
ones,
normal.
yeah, even these ones that aren't normal, you see by 10 already, they're pretty normal, correct? So the question is, what is the rule of thumb that we should use for how large n has to be considered normal? The general rule of thumb, which I'm looking for here, is 30. I'm just looking for it to say it in the book. Well, let's go back up and see if we can find it. First, how do I clear all this nonsense that I have written down? So annotate, clear. All right, so let's take a look. How large a sample is needed for it to be normal depends on the population. Okay. So here's an example. This is certainly not normal, very skewed to the right, correct? Very skewed to the right. And here are samples of size 100. Size 100, already you can see it's very normal. So that's just an example. Let's take a look.
I have a quick question.
Yeah, go ahead.
So with n, right, that is the sample size?
Sorry, yeah, lowercase n is the sample size, that's right.
Okay, and I guess what I'm struggling to understand is that with an increase of sample size.
Yeah.
Oh, never mind. I just thought about it right now. Okay, I get it now. I get it.
You get it? It makes sense?
Yeah, yeah.
Okay. So it doesn't really give an answer, which is kind of strange. Most books do and say it's about 30. I just don't see it written here, which is strange. But hopefully we'll come across maybe in the next section, it'll give us a guidelines. But before that, let's look here. It says thinking about sample means. So it says means of random samples. Means of random samples are less variable than individual observations. They're less variable. They get tighter. And means of random samples are more normal than individual observations. So this is the idea of the central limit theorem. As n goes up, it squeezes in, and it becomes more normal. Exponential distributions are a very important class of distributions. Very important class. So here is the original one. A is the original one. B is a sample of size 2. C is 10. And D is 25. So you can see by 25, even an exponential has become very normal looking. This is just an example. Here's an applet, which may be the same as the one I used. It might be a different one. I don't know. But let's do an example. Let's do this example right here. Example 15.8. Let's do that one. So it says the time in hours that a technician requires to perform preventive maintenance on an air conditioning unit is governed by the exponential distribution, this one here, whose density curve appears in that figure. So it's very exponential. It's an exponential decay. The exponential distribution arises in many engineering and industrial problems, such as time until failure of a machine or time until a success. Okay, let's not worry about that. The mean time is 1 hour, and the deviation is 1 hour. So if I look at 1 unit and 1 unit only, what is the average amount of time that it should take before it breaks or whatever we're looking at? If I look at
1 hour.
1 hour. Now, your company has a contract to maintain 70 of these units in an apartment building. You must schedule technicians' time for a visit to this building. Is it safe to budget an average of 1.1 hours for each unit? Or should you budget an average of 1.25 hours? So remember, even though on average each one takes 1 hour, there's always going to be some variation. Some will take less, some will take more. If I look at 1 unit, it's going to have a certain variation. If I look at 70 units, then the average should have a much smaller variation, correct? This is the idea of the central limit theorem. So if I was making a house call for 1 unit, I might need to use 1 hour and 1.25 hours. But on the average, it's 1.1 hour enough. So let's do the math. So let's look at the plan. It says, we believe that the manufacturing and distribution process associated with this type of air conditioning unit is such that variation from 1 unit to the next is random. That one appliance, one of the pieces, has no effect on the next one. Does that seem reasonable? Unless they're all coming from the same plant, maybe they were on the same manufacturing line or something. Does it seem reasonable that each one should be independent of the one that came before it or after it?
Yeah.
It seems fairly reasonable. Okay, they make thousands of these. So we're going to treat the 70 air conditioners as an SRS from all of the units of this type. In other words, we're going to say that the 70 that are in this building could have been any of the 70 that were produced by this company. Any 70 was equally likely as any other ones. Therefore, it's an SRS. So the question is, what is the probability that the average maintenance time for 70 units exceeds 1.1 hours? The probability that the average time is greater than 1.1. This is what we're looking for. The probability that the average time, T average, is greater than 1.1. So the original curve is not a normal curve, correct?
Yeah.
Okay.
Right.
The question is, are we allowed to approximate this with a normal curve?
Yes,
Why?
because it's a random sample.
That's not the reason. Anything's a random sample if I make it random.
Oh, okay.
That's not the reason why I'm allowed to. It's because remember what the central limit theorem says. As the number of observations increases, it begins to look more and more normal, correct?
Right.
Yes.
So we
correct.
saw on the applet that already by 25, pretty much every curve was looking normal. And here we have 70, right? So 70 is certainly large enough that we can assume that we are dealing with a normal sampling distribution. Okay, so let's compute the z-score for t average. How do you compute the z-score? You subtract the mean and you divide by what?
Sample size.
Well, what's that?
The 70.
1 second. What's z-scores in general? How do we get a z-score? You take your data, you subtract the mean, and you divide by what? This is like a few chapters ago. How do you get a z-score? Who remembers?
X minus mean over standard deviation.
Subtract the mean, and you divide by the standard deviation. What is the mean in this example?
1,
1. What's the deviation in this example?
1.
No, that's for 1 unit. We have 70 units.
Oh, so would it be 70?
It would be what? What's it going to be?
Would it be 70?
The deviation would be 70?
0.32.
Never mind. I'm sorry.
It's okay. No, neither of
Wait,
those are correct.
No.
Just give me a formula. Let's not worry about the math calculator yet. How would I compute the standard deviation from a formula?
1 over square root of 70.
1 over the square root of 70. Excellent. Does that make sense? That it's 1 over the square root of 70? Sigma over the square root of n. In this case, sigma is 1. They gave me that in the problem. And n is 70. So it's 1 over the square root of 70. So I have this. I computed my original problem into a z-score situation by subtracting the mean and dividing by the standard deviation. Well, what is 1.1 minus 1 divided by 1 over the square root of 70?
You asked what 1 over the square root of 70 was, right?
No, I said, what is 1.1 minus 1 all over 1 over the square root of 70?
0.01195.
That's 1.1 minus 1 all over the square root of 1, all over 1 over the square root of 70 is how much?
0.01195.
That's not what I got. That's not,
1.0857.
that's not what I got.
0.8368.
Oh,
That is what I
but
got.
the square root.
Huh?
I
That is
forgot
what
to square root 70.
well, that explains things. So what I have now is this. I have the probability that z is greater than 0.837. So how do I calculate the probability that z is greater than 0.837? How do I calculate that?
you repeat that?
How do I calculate this? The probability that z is greater than 0.837. Anyone?
You use the z-score table?
I could, or I can use,
Crunch it?
yes. Let's use crunch it. I don't need this anymore. So let's go to crunch it, new. So we're looking for normal. It's z, so mean 0, sigma 1, and I1 greater than 0.8366 is what I had on my calculator. 666. So it gives me that there is approximately a 20% chance that I will need more than 1.1 hour per unit. .2014. Oh.
AX macron greater than 1.10 hours equals 0.2014 AX macron greater.
That was so cool. I don't know how that happened. That was awesome. So here we have it right here. The probability that the average is greater than 1.1 hours is 0.2014. And now someone said that we do the same thing with 1.25. Well, should you budget an average of 1.25 hours? What's the probability that it takes longer than 1.25 hours? If I did exactly the same thing, that's a 2% chance. So it's very unlikely to take more than 1.2 hours. But it's fairly possible to take more than 1.1 hours. So I would probably budget 1.25 hours because it's kind of unlikely to take more than that. Does that make sense? We should do more problems like these. So let's stop here.
Professor,
And we'll, yes?
is there a purely software way of accomplishing this? Or is it you're doing half the problem by hand always?
No, you can go to your TI-84.
Okay.
Well, the one thing you have to do is calculate 1 over the square root of 70, because that is the denominator. So unless you can put in the square root of 70 to a calculator, you would have to do a little bit of writing.
Okay.
All right, so we will do a little more of this on Thursday before moving on, because it does take a little time to digest. So that's it for today. I will see you all. I'm going to stop recording. I'll see you all on Thursday.